In this segment, we're going to explore the E1 elimination reaction mechanism. In the E1 reaction mechanism, remember that the rate limiting step, the slowest step of the mechanism, is unimolecular. That's why we put the 1 in there. The rate limiting unimolecular step is the first step of the mechanism where the leaving group leaves to form a carbocation. And that should draw some reminder in your mind of what happens during the first step of an SN1 reaction mechanism, where the first step is that the leaving group leaves as well. Eventually, the E1 and SN1 routes are going to diverge, with the E1 elimination reaction route finishing up with the formation of the alkene product, while the substitution reaction finishes with the attack of the nucleophile on the electrophilic carbocation. So let's take a look at, in this segment, focusing on the E1 elimination reaction, which does certainly compete with the SN1 reaction mechanism as well. So we'll take a look at the mechanism for the reaction that I have shown here on the screen. So we're going to try to go through the steps required to go from reactant to product here for this particular reaction. So remember that the rate limiting step of the mechanism determines the rate, and so we can write the rate equation as K times the concentration of the molecule that's bonded to the leaving group, because the rate limiting step is the slowest step of the mechanism, is the first step where the leaving group breaks away. So let's go ahead and show that first step of the mechanism, which looks identical to the first step that we saw for a nucleophilic substitution SN1 reaction, which is where the leaving group leaves, or the leaving group breaks away. And I'm going to go ahead and label that as our rate determining step, because that's what drives that rate equation that we've listed in red up top there. So we'll go ahead and write out our starting material here with our chlorine leaving group bonded to it. That's our electronegative atom there that's going to be relatively stable once it breaks away. So leaving group breaking away here at our rate limiting step, we'll show the carbon-chlorine bond break. The electrons go with the chlorine atom, because that's going to give the more stable product than trying to break that carbon-chlorine bond and taking the electrons onto the carbon. The chlorine definitely wants those electrons more than the carbon does, so the chlorine's going to take those. And then that's going to leave us with a carbocation intermediate right here. So we'll go ahead and make our carbocation intermediate. So now we have our trigonal planar carbocation intermediate that we have formed out of this. And at this point then, what we're going to do is look for carbocation rearrangements. Because just like with the SN1 reaction mechanism, E1 reaction mechanisms, if we form a non-stabilized carbocation, meaning if we form a primary carbocation or a secondary carbocation that isn't stabilized by resonance, then we need to be looking instead for a hydride shift or a methide shift to stabilize it. So we ask here, have we made a tertiary carbocation? If the answer is yes, we can move on with our lives. If the answer is no, we should look at whether we can do a carbocation rearrangement to stabilize this. So the answer is that this is a tertiary carbocation, and therefore we don't need to do a rearrangement step, but I am going to make the note here to look for rearrangement, or look for the necessity to rearrange. In other words, can we move a proton or a methyl group over by one spot toward that carbocation in a 1-2 shift in order to make a tertiary carbocation out of a secondary carbocation? If so, that's energetically favorable and you would want to do that. Not necessary in this particular example, so don't do it. Now the next step of the mechanism is going to be the beta elimination. So just like we saw with the E2 reaction mechanism, when we talk about the beta position, that's going to be the beta position relative to where the leaving group left. And so we can go ahead and draw in our structure here of our carbocation. Go ahead and plug in our positive charge. So we refer to that as being the alpha position, and all the adjacent carbons are the betas. So beta right here, and beta right here. And I'm going to go ahead and fill in my hydrogens at each of those positions. just to make sure we're keeping accurate track of what's going on here. So we fill in our hydrogens here. 1 hydrogen is all we have room for there, and 1 hydrogen here to fill the octet on that. Now what we do at this step, step 2, is we have our base come in. And our base, as we look up top, remember that our base can be anything that has available lone pair electrons. And so our CH3OH, our methanol, is what's going to act as the base here. Now don't start thinking that methanol is a really strong base. It's a covalent compound. There's no formal charges on the oxygen. So this is definitely a weaker base than, say, sodium methoxide NaOCH3, where the oxygen would have an anion. Methanol is definitely a more stable molecule than sodium methoxide, and hence it is definitely a weaker base, but it's still able to do the job here because we have a relatively unstable carbocation that is eager to become stabilized. One way it can become stabilized is by reacting to form that alkene group through beta elimination. So oxygen lone pair electrons come over. They're looking for a proton to grab. We have 3 different possibilities here, and this is the step in the mechanism where we definitely want to follow Zaitsev's rule. So in segment 57, we looked at Zaitsev's rule, and so if you aren't familiar with that, it would be a good time to go back and watch or rewatch that to get a handle on Zaitsev's rule. But it says that we need to remove a proton so that we can form the most stable alkene group possible in the final product, and the most stable alkene group is the one that is most substituted. So we want to remove a proton here such that our final alkene product will be the most substituted alkene possible. And to do that, we're definitely not going to remove this proton because that's not going to lead to the most stable product. Instead, what we're going to do is head up to here to grab this proton, or alternatively, we could have also grabbed this proton here on the lower left. Since those are 2 symmetrical isopropyl groups in this molecule, grabbing either one of these 2 protons, the starred one or the one that we have the arrow to, would end up giving us the same product one way or the other. So I'm just going to grab this one up here, break the carbon-hydrogen bond, and those electrons are going to come down to here. No need to break away a leaving group from that carbocation because the leaving group is already left. So essentially what we're doing here in the the E1 reaction mechanism is we're breaking the process into 2 steps. First, the leaving group leaves. Secondly, the base comes in, grabs a proton, and the carbon-carbon double bond forms. Whereas in the E2 reaction mechanism, we were doing all this as a single simultaneous step. So let's go ahead and write out our product that results from this. So our product that will result here will correspond to installing our carbon-carbon double bond right here. So therefore we're making an alkene group that has 4 alkyl substituents. 1, 2, 3, 4. It doesn't get any better than that by Zaitsev's rule, because Zaitsev's rule says the more alkyl substituents the better. We've got 4, can't ask for any more. And the other product of this reaction step would be our CH3OH2 with a positive formal charge on the oxygen. We would describe that as our conjugate acid because our base, CH3OH, grabbed a proton to become that conjugate acid product of this step. So that's going to be step 2, our final step of the mechanism. What you will notice here at step 1, where the leaving group broke away to give a carbocation, since that was the rate limiting step, we can focus on that to think about what would allow this reaction to take place better, take place faster. Much like with an SN1 reaction, this step, and hence the whole pathway, is going to go best if we have a more substituted carbon atom. So that carbon atom is bonded to the leaving group, in other words, this one right here, the more substituted that carbon is, the better. In other words, if it's a tertiary carbon, it's going to react fastest. Secondary carbons react second fastest. Primary carbons hardly are able to follow this mechanism, if at all, because they give way to such unstable carbocations. So one of the golden rules of organic chemistry is don't form primary carbocations unless there's resonance to stabilize them. So no resonance here in this type of problem at the moment. So primary carbons are not going to give way to carbocations here. So tertiary carbocations give the carbocation the fastest. just like they did in an SN1 reaction mechanism. And then what happens is once the carbocation forms here, at this step, that's where you start to get competition going on between elimination in step 2 of the mechanism, which is what we show here, and substitution, which would be where the methanol acts as a nucleophile, meaning that it is going to form a bond between the oxygen and the carbon atom. So what we're going to look at in a later segment is what will drive a reaction toward preferring to do an elimination reaction or a substitution reaction. But for now, we'll leave it just as they will be in competition. And so whenever you do a substitution reaction, you'll likely also get some of the elimination product as well out of that reaction. Let's take a look at one more example problem here of the E1 elimination reaction mechanism to make sure that we have a handle on how to go about doing this. In this reaction, I highly advise you, once I go ahead and write this out, to go through and think about what you would come up with as the answer for this by hitting pause, and then go back and watch me go through it to make sure that you are on the right track with this. In this problem, we're asked to provide a mechanism and predict the major organic product of the following E1 reaction. So definitely when looking at reaction examples, pay attention to the clues that you're given in the text. And the clue you're given here is that it's an E1 reaction. So we need to predict anytime you see the term elimination or E1 or E2, that the product had better have an alkene group in it. So let's take a look at the mechanism for this to go through this problem. So first things first, the first step of E1 reaction mechanism, remember that E1 means the rate limiting step, is the formation of a carbocation where the leaving group breaks away from our starting material. So the first step here is going to be that we break away that bromine, and that's going to be our rate limiting step, is the bromine leaving. The bromine is our electronegative atom, therefore it is our leaving group. That's the weak bond, is the carbon-bromine bond, and it's going to lead, by its breakage, to the most stable possible product by breaking a bond in this starting structure. Because that bromine is fairly happy to end up with the negative formal charge it's going to be carrying here, because of the fact that bromine is a very electronegative atom. So it's pretty okay with having that negative formal charge. So our carbocation is going to be right here. And remember that when you form carbocations, you always need to have in mind the possibility of a carbocation rearrangement. And a carbocation rearrangement will occur if we start with a secondary carbocation, and there's some way to do a 1-2 shift, meaning moving a methyl group or a hydrogen from the adjacent carbon atom over in order to convert that secondary carbocation into a tertiary carbocation, because that's going to make that step energetically favorable by going from a secondary carbocation, which is less stable, to a tertiary carbocation that is more stable. So in this second step here, on the lookout for carbocation rearrangements, we take a look at our secondary carbocation carbon right here. And indeed, we have a couple of methyl groups next door at what we would refer to as the number 2 position. So remember that we call the carbon atom that's the carbocation position 1. The adjacent carbon atoms are position in 2. And if we have any methyl groups or hydrogens bonded at position 2 that could move over in order to create a more stable tertiary carbocation, that's going to be a favorable thing to do. So what we're going to do is move one of those 2 methyl groups from position 2 over to position 1 in a so-called 1-2 shift. So we take the methyl group from here, bring it over to right here, and we'll go ahead and write out the intermediate that would result from that, which would be a tertiary carbocation now. Make sure that you have indeed formed a tertiary carbocation, otherwise this is not going to be a favorable step to take place. For the energy to be on your side, it has to go from a less stable carbocation that's a secondary carbocation to a more stable tertiary carbocation. So we will have moved that methyl group over by 1 spot. I'm going to show that methyl group in blue right here. And keep in mind that the reason that we're able to do that is this is a carbocation right here, so it has just 1 hydrogen there. And once you move that methyl group over, now we have a complete octet at that carbon, and the positive charge has moved as a result over to right here, because now that carbon is the one that only has 3 bonds to it instead of 4. So now we have set up this molecule with our carbocation, And since remember we said we're doing an elimination reaction, what that means is that next up we need to find within our reaction mixture something that can act as a base to grab a beta proton. So step 3 is that the base is going to remove, or in other words, abstract a proton from the organic molecule, from our carbocation. And specifically, it's going to abstract from the position that is beta to the carbocation. So the carbocation we consider to be at the alpha position. So beta is going to be any adjacent carbon atom. So therefore, we could abstract a proton here. That would be beta. Or here. That would be beta as well. We want to follow Zaitsev's rule here. And there's a third possibility there for beta position right there, by the way. So we want to follow Zaitsev's rule when we think about where we're going to remove that proton, because when we remove the proton and make our carbon-carbon double bond, we want to create the most substituted possible product. So thinking about where those carbon-carbon double bonds could go, we could put the carbon-carbon double bond right here, or can we? So hopefully you realize that if we put the carbon-carbon double bond right there, that's going to create a carbon atom right here that would have 5 bonds to it. That is an absolute never, never, never rule. Never make a carbon with 5 bonds to it, so definitely not there. We are over the limit there. We could alternatively, by removing the proton right here, we could put the carbon-carbon double bond in there as an option. And then as our last possibility, we could put the carbon-carbon double bond right here. Well, what's going to turn out if we were to look at exactly the structures resulting from all 3 of those beta positions? Then what will result is that we put the carbon-carbon double bond right here to give the most substituted product. So our water is what we have available to act as the base. Looking back at our reaction mixture, that's the only thing that we have as a source of lone pair electrons here in abundance. So the oxygen atom's going to come in. It's going to grab the proton right here, forcing that carbon-hydrogen bond to break, and those electrons to come over to make the carbon-carbon double bond, thereby giving our alkene product. So let's go ahead and write out the final product of this reaction. Methyl group right there, carbon-carbon double bond newly installed there, and then our tert-butyl group coming down to right here. So another thing that I very often like to do is include extra tidbits in the problem, such as name the final reaction product. So now's your opportunity to test your skills at coming up with the name for this particular product. And in coming up with the name for this particular product, I'm not going to ask you in this particular example to specify the stereochemistry, because we haven't really discussed whether the E form of the molecule here is the product or the Z form will be more preferable. So therefore, we're not going to mention whether this is the E form or the Z form, because we haven't talked about what in actuality would be preferred here, the E or the Z. So come up with the name for this molecule, but you don't need to specify the stereochemistry for it. And I encourage you to hit the pause button as usual, see if you get the name for it down, and then check your answer with me. All right, so to come up with the name, we find the longest carbon chain. The longest carbon chain that we can map out that has both of the carbons of the alkene group in it would be this right here. We start numbering that chain, starting from the end closer to the alkene group. So starting numbering from the end closer to the alkene group, we could start numbering here, 1, 2, 3 in green. Or we could start numbering from the other end of the chain, going 1, 2, 3 in blue. And oh dear, we have a tie. So how do we decide which end we actually start numbering at then? The criteria we then use is that since there's a tie for which alkene direction to go from, we go then based on where we can start numbering to put a branch closer to the end. And starting numbering based on our scheme in green is going to put a branch closer to the end. So we'll go with that. But remember, the first thing you look for is where the alkene group is. You want to put the alkene group as close to the end as possible. And it's only if there's a tie that you want to look at where the branches are. So we'll go ahead and fill in our numbers here. And based on our numbers, our parent name is going to be 3-hexene or hex-3-ene as an alternative to that. So 3-hexene. And then we need to fill in all of the branches, and we have a bajillion methyl branches here. Well, maybe not quite that many, but several methyl branches. So we have 4 methyl branches. So that's going to be referred to as a tetramethyl. And we need to specify where those 4 methyl groups are. So we would specify them as being at 2, 2, since there's 2 of them at position 2, 3, 4, and I'm running out of room here, tetramethyl, and then a dash to separate that 3 from the word methyl, dash hexene. So that's going to be the full IUPAC name for this molecule without stereochemistry. So now that we've concluded this segment, you should be comfortable with writing the E1 elimination reaction for the combination of some molecule that's able to act as a base, meaning something that has a lone pair of electrons, and these are not necessarily going to be strong bases. More often they are very weak bases, and show the reaction of that base with a molecule that has a leaving group to give an alkene product, or a so-called elimination product.